Welcome on the talk Low-Level Userspace Programming. I am Petr Baudi, and today I'd like to talk a bit about the kind of system programming that's not frequently covered, because usually you either program in the kernel, you work on device drivers, or you work on some virtual memory management or whatever else, or you work on the application programs that draw pretty windows or are some network applications or so on. And today I'd like to talk a bit about what's between these two layers, what happens in the user space at the lowest level, how can you communicate with the kernel, and how can you do some neat things in the user space without much kernel help. This talk has been marked with that ninja logo, but I don't think you really need to fear that much. I'll be showing you some actual code, and maybe there will be even a little of assembly in there, but I'll be covering a lot of or several smaller areas, and if you just start to drift away and get lost in one area, the chances are good that in a few minutes you'll be talking about something else and you'll catch up again. So don't really worry if you get lost in one part, and I don't expect you to remember all that's said here, but I think for a good Linux programmer, it's important to at least hear once about some of the concepts that I'll cover here. What will we talk about? We will talk about the kernel interface in the user space. So what happens if you make a syscall, if you ask the kernel to do something for you? We will talk about what is actually a program, how the file with the program looks like, and how can you inspect that file, how can you manipulate that file, how do shared libraries work, and what is a dynamic linker, and so on. And we will cover some interesting system calls that can enable you to do some neat things. We will cover the mmap syscall, which you can use to set up some kind of memory that is mapped to a certain file, or just as kernel for memory. But it doesn't have to be regular memory. It can be some interesting memory, like the GPIO pins of a processor or whatever. I'll show you how to run code that was never meant to run in Linux in the user context. So we'll actually see how Wine works, how DOS-EMU works, and how can you take some code, for example, maybe even from some, the code can be for just running standalone, or it can be designed for some other operating system, and how to set up the context of the Linux process to actually be able to run this code that was never meant for Linux. And we will see how to manipulate with already existing processes, and how to stop them at will, or touch their memory, or change the processes, and so on. So this is how, for example, the GDB debugger works, the strace tool works, and so on. We will take a look at at how that works. All right. So I expect that you have seen some C code before, and that you have some user level experience in Linux, and of course that you already programmed some software in Linux. I'd like you to ask questions if something is really not clear, but somehow people never really tend to do that. So I don't know, maybe this will be the first time that people will ask a lot of questions. The purpose of this talk, why I am giving this talk, is that I'd like to share some experiences with you, and mainly encourage you to actually don't be afraid to look at the code. Because, well, when I was 13, And a good friend of my father, Pavel Troller, introduced me to Linux and helped me install Linux on my computer. I was learning how to do shell scripting and so on. And I was learning some basics of the C language. I thought that format strings are a really stupid idea back then. And I was wondering how to make some nice-looking text interfaces, like how to write text on a specific position on the screen and so on. So I've heard this. And he told me, well, look at the code. The Linux kernel is open source, so you can just look at the TTI device driver and look at how that works. So I have spent 2 days of being totally miserable, but finally I found the code that does this, and I've deciphered how to do this escape sequence. And it's been actually a great experience for me because even though I didn't really know C very well, I was finally able to find the code to find the code in Linux, and I think it's been actually in the long run better advice than to tell me just look at the documentation or whatever. Of course, that will be much easier. But this way I learned so much in the 2 days that even though I felt really miserable when I was searching for this, well, it's been a great experience, and I'd like to show some pieces of code here today if we'll have enough time, so that also you aren't afraid to actually look at the code that does these things. Because then you will be able to solve problems that you would never be able to solve before. Okay, yeah, we won't really need that much assembler, but if you want to do some system programming or just be able to debug even very unwieldy code, it's useful to know just the very basics of assembler. Assembler it's not really a programming language. Well, it is a programming language, but in a normal language, you write some high-level commands, and they get translated to instructions, which are executed by the processor. In assembler, you are writing directly the instructions that are executed by the processor, so you need to know exactly how the processor internally operates and which registers the processor has, how does it access memory, and so on. And if you want to do something, you need to explicitly fetch some data from memory, do the transformation on the data, and then explicitly put the data back into the memory. You need to manage your registers and so on. But you can do anything that the processor allows. Often it's okay, you have some program and you can't figure out what the program does. And sometimes it's not so outlandish idea to actually look at the assembly code of a specific function in the program which does the weird thing that you wonder about. And I won't really go into the details of all instructions, but I should at least explain that piece of that short piece of code that's over there. The push A instruction stores basically all the registers, the whole state of the processor to a stack, so you can modify the state, and then later at the end with the pop A instruction you can recover the state. The mov instruction sets the content of the register EAX, which is kind of like the first register of the processor, to value 1. The third line is a bit weird. Do you know the XOR bit operation? So who knows what that third line does? Okay, some of you do. You take the content of the second register, the EBX register of the processor, and you XOR it with itself. And the XOR bit operation works in such a way that if the bits that you are XORing are the same, the result will be 0, and if they are different, the result will be 1. So if you XOR some value with itself, then all the bits will be the same. So result of that will be 0. So that third line actually sets EBX to 0. It's a kind of weird way to do things, because you would expect that just the same line as the second one would be used, and you just use 0 except of 1 there. But this is actually, well, just more efficient way to write this. It takes less memory to write this. So traditional compilers will produce rather this instruction than explicitly moving constant 0 to the register. Okay, the fourth line is kind of special because that makes a syscall. It triggers a software interrupt, and the kernel will catch that interrupt, and you will, at that point, your program will stop, and the kernel will take over and do whatever you want it to do. So here, the EAX is the ID of the syscall that you want to do, and I admit that I actually forgot right now what number is the syscall number 1. Can anyone help me out here? I see a lot of kernel hackers here. Surely they all know the syscall numbers by heart. Oh. So who can find it fastest? Well, meanwhile, traditionally syscalls will return the value again in the first register of the processor in EAX. So they and by the exit syscall. Okay, cool. So using this, you exit the program with return code 0, because EBX is the first parameter of the syscall. So using this code, you will exit the program, and actually the last 2 lines will never get executed. So I don't know why do I have them in there. Okay. Anyway, maybe you just got the general idea of how the assembly code works, and of course, if you will ever need to use it, you will need to look at some more documentation. But maybe this will be a bit helpful. Yeah, and I won't go into the details of this because you would be here for a long time and you would be very bored. And I'll skip this as well. Okay, so I promised to cover how syscalls work, and let me check the time. Okay, basically, the kernel does its things. It manages the hardware and talks with the display and the keyboard and writes data to the disk and so on. But its main purpose is to run programs, of course. And the programs use the services of the kernel, and the kernel actually has a lot of interfaces to the programs that the programs can use. But of course, the primary interface is the syscall interface. So when we say that we make a system call, that means that we, from our, for example, C code, we run some function, and usually the glibc, which is the C library, which provides the basic environment for C programs. It implements functions like printf and square root and so on. It provides these functions, and most of the time, these functions are actually very thin wrappers that do only one thing, and that is give control over to the kernel and let the kernel do its thing, and then when the control returns, pass the return code from the kernel back to the program. So actually, most of the code of the syscalls is auto-generated. Only some syscalls have some special compilability code and so on. But what actually does on inside the glibc, you need to, in some way, let the kernel know that you want it to take, you want it to take over. So there are actually several ways to do that, because, well, the at least, well, I should know that a lot of this is Intel specific, so it's specific to the PC platform x86 and some of it to x86-64. Of course, for example, on ARMs, it will all work a little differently, but there won't be very big differences. But for example, this is quite PC specific. And the PC platform has a very long history. So there is a lot of compatibility craft, and only new processors support certain interfaces and so on. And it's the same with syscalls. The traditional way to do a syscall is to do this crazy int instruction, and that's actually kind of remnant from the days of DOS and standalone applications on the Intel processors. It actually runs a software interrupt, which is what that actually does is well, in the real mode, in the compatibility mode of the processor, it looks at the top of the memory. And there you will have list of addresses that will handle specific interrupts. And if the application requires a certain service, for example, to write something to the screen, it will trigger an interrupt. And various parts of the system, the operating system, the BIOS, some extension cards, and whatever, will provide services in specific interrupts. And when the application requires some service, it will trigger a specific interrupt, and the control gets transferred to the code provided by the BIOS. For example, the BIOS does its thing and then returns the control. In kernel, there is just a single interrupt handler. That's this. Its number is 128. And if a process actually does an software interrupt instruction, it gets so-called trapped, and well, processor will see, oh, whoa, wait, you shouldn't do this, you are just an application, and it will transfer control to the kernel, and the kernel will provide interrupt handler, and the interrupt handler will look at the first register, see the number of the in that register, and transfer the control to a specific function within the kernel. Based on the number. So syscalls, so this way, the processor will trap and stop the process at the point it calls this int function and transfer code to the kernel, and the kernel will just run a specific function. So each syscall is actually just a function in the kernel. And if you just grab for the name of the syscall, usually you will easily find the entry point, and you can follow actually what goes on in that syscall if you are trying to understand some corner cases or whatever. Okay, actually because this int instruction was used for different purposes in the past, it's actually not as efficient as it could be. It involves some extra memory lookups to find out exactly what kind of interrupt handler should be executed, what address do we need to jump to, and so on. So newer processors provide some new instructions to do this, and actually, historically, Intel and AMD tackled this at once, and each of them developed its own pair of new instructions, and the instructions don't work the same way, so it depends on exactly what of these instructions your processor supports, and if you are running on an older processor, your processor will support neither. And then the question is, how does the usually kernel shields you from these processor specifics? But well, here we are talking about the kernel interface. So the question is, how does the program know whether the special efficient syscall instructions are supported or not? And the answer for that is, well, the kernel knows. So what we could actually do is for the kernel to provide some few special pages in the memory at some fixed addresses, so that, well, the user space process can rely on the existence of some code at some specific address, which is reserved and cannot be used for anything else. And instead of making a syscall, you will just call a function on this specific fixed address. So this is called, in general, this concept is called VDSO, and it has some other advantages because switch to the kernel is very, very slow. You need to save the complete state of the processors. Sometimes some caches are even flushed and so on. So switching to the kernel to make a syscall is extremely slow. And actually, if you are trying to optimize the performance of your program, you should try to avoid syscalls as much as possible because they will slow you down in a huge way. But for example, to get the current time, you want to get the current time with some precision. Normally, you would make a syscall that enters the kernel, and the kernel just looks up at some memory where the current time is, and then save that to the register and transfer the control back to you. But there is really no reason why the kernel should need to do this. What if you had just this value in some page which was mapped directly to your memory space? So instead of all this expensive transfer of control to the kernel, you can just look at some specific address. And because you are not changing any state, you are just looking up some public value, which you don't even need to care about any security or whatever. So actually, this is, again, exactly what happens. And the so-called VDSO offers several interfaces like this. So instead of calling a syscall, you will just call a function in this special page. And the content of the page, the code of the function is provided by the kernel and mapped to your context so that you just make this call. And one of these functions is actually the vsyscall function, which you will call. And the function will use the best method available for your processor for entering the kernel, for calling the kernel. So if your processor is too old and doesn't support any extra instructions, the vsyscall function code which is provided by the kernel, will just contain the int call. And if your processor is new enough, it will contain the code that uses the best method for your processor. Okay, yeah, there is a lot of other ABIs, and I won't go into the detail. So of course you will realize that you have some special file systems like /pros or /sys, and you have some special kind of files which actually, or at least file descriptors, which if you read, they will provide you with some special data like notifications of events in the system and so on. And I won't really go into the detail, but you can find really a lot of information there, so I recommend reading up on this. Okay, so time to look at some actual hacks. I mentioned the mmap syscall before, and the mmap syscall, what it does is that it's the primary way for programs to actually get memory allocated. So it just tells the kernel, I need some memory. And it tells it what kind of memory it is and how large chunk of memory do you want, if you want it mapped on a specific address or you don't care what address it will have, and so on. And it can be used in two basic modes. It can be so-called anonymous memory, that is, well, just memory. Or it can be mapped memory, and then it will be memory which is actually corresponding to the contents of some file. So then, if you map a file to the memory, then by accessing memory, you are actually reading data from the file. And if you just access the memory, then if the contents of the file isn't read from the disk yet, well, then the kernel will trap your access again, and it will load the necessary data from the disk to the memory, and then, well, return the control back to you, and you will get your data. And it also works for writing. So if you modify the contents of the memory, it will be propagated to the disk. So it's an interesting way to access access files. It has its problems because appending to files is kind of problematic in this case. Because well, if you map some memory that isn't actually on the disk, then well, strange things might happen, and I don't really want to go into the details of that. But it's still very useful. Well, one interesting thing I use this for is to actually map the device file representing the physical memory of the processor. Then you can map a piece of physical memory of the processor to your memory, to the memory of the process. Because of course each process sees different memory. Because the memory is mapped from virtual memory, which is kind of like the image of the world, which is accessible to the process, to the physical memory. Because each process, if you look at the same address in each process will probably see something different, because each process has different libraries loaded and the different amounts of memory allocated on different places and so on. And the kernel or the processor, or they cooperate on that, they handle translation from this virtual memory to the physical memory. And but sometimes it's useful to actually be able to access the physical memory of the process. So there is this special device file, devmem, which corresponds to the physical memory. And if you map a portion of this file, then when you access the file, you will modify the contents of the physical memory. One reason why this is useful is, well, the processor is just a circuit, and sometimes it's useful when you do some low-level programming. It's useful to realize this perspective, and you'll be able to understand some concepts better, I think, if you try programming some microcontrollers where you can directly manipulate the pins of your processor. And at least for me, I've gained a useful perspective on system programming by doing this, and I realized a lot of things that were bothering me and that I didn't really understand about the low-level architecture of the operating system and so on. And nowadays, it's pretty easy to actually do this because, for example, you can buy you can buy a Raspberry Pi or an Arduino or a board like this, and just attach some lights that you can blink with, and read value from various buttons and so on. And this way, I think you will learn to think about the processor in a new way and potentially useful way. Okay. Actually, how is this? For example, do you know the Raspberry Pi? Have you heard about the Raspberry Pi? Who of you have heard? Okay, some of you, not all of you. Raspberry Pi is a small board with ARM processor and some connectors and some video connector and USB connectors and stuff like that. You can buy it for something like $35 or $40. And one interesting feature, it has a GPIO header. So well, you can run Linux on this tiny board, but you can also attach some lights or motors or buttons to the GPIO pins. And if you actually write to specific portions of the memory, you will be able to change the status of these pins, whether these pins are connected to some the voltage source, or if they will be grounded, and on that depends whether your motor will turn, or if your light will shine, or if it will be dark. So all this is done by accessing a special portion of the memory, and well, this mmap call actually does exactly this. So when you open the file, you get the devmem device file, you get the file descriptor, and then you call this crazy three-line mmap call, which actually, well, let's take a brief look at the parameters. The first parameter is the desired address where you want to have the memory mapped. We don't really care here if what value the pointer to the memory will have. So we just put null there and let the operating system decide whatever suits it best. The second parameter, GPIO block size, is how much memory we want. So how large chunk of memory do we want mapped? The third parameter is what kind of things do we want to do with the memory. Here we want to be able to read from the memory, to check the current state of the GPIO pins, and to write to the memory, to change the value of the pins or the mode of the pins, and so on. And what's missing there is one other thing that we could have want to do is execute code there. Of course, that's a nonsense for area which is reserved to GPIO pins, unless you want to run code on your Raspberry Pi by setting up the GPIO pins in a specific way so that it corresponds to some instructions or whatever. But that's a bit contrived, I guess. But if you map some file, then it makes a difference whether you allow code which is contained in such file to be executed or not. And the next parameter, map shared and map fixed. Map fixed is actually nonsense there. Ignore that, please. But map shared says that I don't want a private copy of this memory, but when I make some changes, I want everyone to see these changes. This actually makes a big difference, and actually, like 2 months ago, I was at the customers and we were debugging some AMAP using code, some user space PCI driver, and after 4 hours, it turned out that the mistake was that they were mapping the device memory using not map shared but map private. And if you map some memory with map private, that means that when you change that memory, only you see these changes. So if you modify that memory, a copy of the original page is made, and from then on you are on your own playground and you can make changes, but no one else will see the changes, and the changes will not be propagated back to the file. So in this case, back to the memory. But we want the changes to be propagated back to the memory. That's the whole point. So we use the map shared flag. Okay. Yeah, memfd parameter means that, okay, we want to map memory from this file, from devmem, and the last parameter is the offset. So the GPIO pins are controlled by a memory region at a fixed address, and that address is stored in the GPIO base constant. So this is how this works. And well, memory is a wonderful place. And actually, well, okay, that one was some tiny ARM board, but even on your PC, this might be useful because sometimes, well, I agree that it's a bit dubious practice, but sometimes you will meet it, and sometimes it's used that a driver for some device, for example, for some PCI card, is not implemented in the kernel, but it runs in user space, and sometimes it can be useful for quick prototyping of drivers or whatever, just learning how the device works before you start actually touching the kernel code and with all the worries associated with that. Actually, each PCI card that you have in your PC provides some memory. Sometimes it uses that just to talk with the rest of the computer. So it provides some memory region, and if you write something to that memory region, the card interprets that as a specific command, for example, transfer data, receive data, whatever, and then if you write to some different place, it will set the parameters of that. Or for example, your graphics card provides its video memory also as a memory region, and this is advertised in a standardized way. on the PCI bus, so your kernel doesn't really need to recognize the device. You don't really need any driver for that, but you will still be able to access these regions using that file in the /sys directory. And if you look at it, it looks like a regular file. Its size corresponds to the size. Its size corresponds to the size of the region. And again, if you open it and mmap it, then if you write something to it, it gets actually written. The data actually gets sent to the card, and the card can recognize it as a comment or whatever, and then you can read bytes back and talk with the card like this. Yeah, and again, I repeat, be careful about map shared versus map private, or it won't really work. Yeah, there is actually a useful command line utility for that as well. The URL is here, PCImem. If you just Google it, you will find it easily. Okay. Oh, I'm going way too slow. Okay, so, well, just briefly about the format which is used for the binaries, the programs of the system. It's called ELF, or Executable and Linkable Format, and it's actually a very interesting invention because it's a single format which allows all kinds of runtime data to be stored. It can be code of a program. Well, by code I mean compiled code here. It can store executable programs. It can store shared libraries. It can store core dumps. It can store intermediate object files which are used for further linking and so on. And it's all just a single format which is very flexible. And the thing you should remember that there are sections, and the sections describe information which is required for linking. For example, there is a section, there is a so-called text section which contains the actual code. There is a section with program header which contains some useful general description of the program, and there is a section which contains list of all symbols that it depends on. That means for example, if you have a program which calls the print function call, the formatted print, then, well, of course, the program doesn't provide this function call itself, but it depends on an external library for that. So there is a special table which contains the print label and says, okay, for this program to work, we need to have something linked in some shared library or whatever, which provides the print function call. So it has tables like this, and it also has so-called segments, and segments describe how are things actually loaded in the memory when you want to run the program. So it describes, okay, I want this data loaded here and that code loaded there, and so on.
Pascal, to avoid confusion, you should probably say that the sections and segments overlap. So
yeah, of course. You have a text section and the text which contains the code, and of course the text section is also part of some segment because you really want this loaded in the memory. But you can have multiple segments because, for example, you want an executable segment with the code, some read-only segment with read-only data, and read-write segment with runtime data, and so on. Okay. Okay, I should go faster here. So I actually wanted to show you the code which does this, but I don't really have time for that. So, well, you have some file names in the kernel that you can actually look at if you want. You just, well, if you want to execute the program, of course, first you need to create a new process. If you don't want the new program to substitute for the original program. If, for example, if you are starting some program from Midnight Commander, then Midnight Commander needs to create a new process so that Midnight Commander keeps running while the new program also runs. So first you create a new process using the fork system call, which will make DOS game, and we would like to run this game just as a Linux process. It actually isn't as difficult as it seems. Okay, so we take the exe file of the game, for example, and we manually perform all the relocations which are contained in the header of the elf file, of the exe file, and all the rest is just code that we could be able to run directly, right? The only problem is that, well, okay, maybe it directly accesses some kind of hardware and it directly draws all the sprites and all the graphics to some kind of frame buffer, and it calls some interrupt routine to get the current position of the mouse and so on. But actually what we can do two things. We can find some problematic parts of the code and patch it, of course, by just replacing the instructions, but that's kind of boring. There is other interesting things we can do. For example, if the program accesses the graphics memory, okay, we can use, for example, SDL, which is a pretty well-known graphics library, and it allows us to allocate a frame buffer, which is an area of memory where we can write to actually make pixels show on the screen with the right colors. And one thing we can do is we can use the mmap system call to request the frame buffer at a specific place in the memory, which is compatible with the place where the graphics card puts it in the DOS. Another thing is, okay, what about the interrupt routines? For example, if the DOS game wants to open a file or get the current position of the mouse, it executes some instructions which would normally be trapped, and the Linux kernel would just kill the process because the process did something it doesn't have permissions to do, and which really doesn't make any sense in the Linux context anyway. But okay, how does the kernel kill the application? By sending it the segmentation fault signal. And well, we can insert our own signal handlers for most of the signals, including segmentation fault. And actually, it isn't really very well documented, but normally the signal handler will get just a single parameter with the name, with the number of the signal received. But for some signals, you can there is another parameter that you can receive, and that's a special structure which will exactly describe where this segmentation fault happened and what was the value of all the registers. So if the binary makes a call to the DOS operating system, that will be trapped at that point, and you will get the segmentation fault. But in that handler, you can look at the particular code there and look at the value of the registers, and you will know what kind of interrupt or what kind of instruction happened, and look at the registers and actually emulate this code and set up back the registers to the correct return values and return control back to the program, and the control and the program, even though it received a segmentation fault signal, can run merrily on. And there is other tricks like this. So, but custom segmentation fault handlers are actually very useful, and you can even use one to, for example, print out the backtrace of the program and so on. Okay, and the almost last slide is. Well, this is the last system call I would really like you to know about, because it's useful to know how does, for example, the strace tool or GDB work internally. I don't know who here ever used the strace tool. Okay, almost everyone. For those who didn't, this is, for me, it's perhaps the most essential debugging tool I use. If some program misbehaves, it can be any program, it can be an application program, and I've never seen the sources, but if it fails mysteriously, often the easiest way to find out what actually goes wrong internally is to run it using strace, because strace is a tool which runs the program, but traps all the system calls the program makes, including the parameters, so you can exactly see what kind of files the program tries to open, if that succeeded, what kind of data it writes there, and so on. And often, if, okay, the program says it cannot open some file, or or cannot write some data somewhere, then the way to find out exactly what goes wrong and be able to repair it is to run it using strace, and strace will give you all this information. And how does it? And actually, strace is kind of interesting in that it can also attach to an already running process. So you have some daemon which is running on the background, and it does something weird, or it starts consuming 100% of the CPU, and you want to know what's going on. Did it get into some infinite loop, or is it trying to repeatedly read from some file or whatever? Again, if you use strace, you can attach to this process, and you will immediately start seeing what kind of system calls it calls. So the way this internally works is using the ptrace system call, and well, it's system call which is kind of famous for the amount of security holes that are actually contained in it. So sometimes it's actually even disabled, but I think there are some. Yeah. I think in some versions of Ubuntu it's disabled, but well, I hope there is some way to re-enable it. Otherwise, tough luck for the Ubuntu users. Just move to Debian or OpenSUSE, okay. And the ptrace call allows you to manipulate with running processes, like totally manipulate with them. You connect to them, you stop the process, and using ptrace calls, you can inspect the current value of all the processor registers within the context of this process. You can single step the process instruction by instruction. You can let it run until the next syscall and just trap at that syscall. You can write to memory of that process. And actually, you can do pretty neat things using that. For example, OK, you run some program, and then the program runs longer than you thought, and you need to go away already, but you would like to see what the program did when you are back home, but you forgot to run the program inside a screen or a similar tool which allows you to attach back to attach the program back and look at its output. One thing you could do is use ptrace to overwrite some currently running code in the program with instructions and system calls which will change the terminal, the controlling terminal and standard input and output of that program from its current standard input and output to your new input and output, for example, of your SSH session that you started when you went back home. So, of course, doing that manually with ptrace sounds pretty scary, but there are tools which can do this for you already. But how they work is exactly using ptrace. They use ptrace to replace existing pieces of memory in the running process to run the code they want it to run, which will replace the file descriptors and then give the control back to the program. And ptrace is a very useful tool for that, to allow this kind of manipulation. Okay, so. Yeah, I promised you some commented code tours, but it turns out, well, I would need at least extra half an hour, which is not something that the schedule allows for. So tough luck. If you are really interested, then we can make some additional session where we can look at some of the details, whatever interests you. Okay, so that's all from me. And I wonder if you have any questions, or I don't know how this works. I scared everyone too much. Okay. There is a question.
Hey.
I once searched for a method, is there a binary to easily read out defmem, which also gives you some comfortable options to whatever. I found some code, or it's easy to make up yourself, but is there something...
What do you mean by comfortable options? You can use some kind of hex editor.
Dump a whole memory area, dump whatever, just that you can use it, just that you don't have to make up your own C program.
Well, yeah, I think the best way to do that is just use some hex editor, which has enough capabilities to do this. I can do a shameless plug here. There is a hex editor that I wrote some time ago, and Libor maintains it now, and it's it's called Het, and it's kind of one of the possible tools which could do this. But I think other hex editors can work as well, because you can use the hex editor to jump at a different, at a specific offset, and then you can select the memory region that you want. Okay.
I'm afraid we are done.
Well, I think that's a good thing, because
things after this one. Pasky, maybe you could set up a workshop in one of the meeting rooms. I think there's one room for casual sessions. So.
Okay, I can do that either this evening or sometime tomorrow. We could do something like this if anyone would be interested. So I guess I'll just try to set up something with the organizers and write the time somewhere. And if you are interested, you can come and we can talk about specific code or walk through specific code and take a look at how things work. Okay, so enjoy your lunch. If you are going to lunch, I think you must be hungry. So. Okay. Já jsem si říkal, jak to si do 3 hodiny noc spát. Témat by byla až